Okay, so good morning everyone. Welcome to the first non-keynote session. My name is Florian. I'm a researcher at NEC Europe, and I want to talk about Uniprof, which is a unikernel performance profiler that can also be used for debugging that I created in the last couple of months. Now, as a bit of motivation, I know I'm kind of preaching to the choir here. I guess most people here really love unikernels. You know, they're small, they're fast. They can really give this new cool kid on the block, Docker, a run for its money in that and still give us the nice features of stronger isolation and so on. But then when you talk to people about, deploying unikernels, often what you hear is that people say, well, unikernels, it's kernels and these are hard to create and debug and I don't really want to deal with this and it's also complicated. And then you might say something like, well, yes, but for unikernels, that's not really necessarily true. You just link everything together in a single binary and share an address space, and that means actually you can even use GDB directly on your unikernel. It's great, right? And while that is true, we are admittedly lacking tools to support developers in creating and maintaining unikernels, such as an effective profiler for them. And this is where Uniprof comes into play. The goals that we set out for was that we wanted a performance profiler that wouldn't require any changes to the code and that would produce only minimal overhead while profiling, so you could actually even use it in production environments. And when you look at these requirements, one of the typical idea that you can come up with is that you want a stack profiler, where you basically just collect stack traces at regular intervals, lots of them, and then you analyze all these stack traces to figure out which code paths show up especially often in them, either because there's a function that takes a long time to run, or because it's just functions that hit over and over and over again. And that can point you towards potential bottlenecks in your code that warrant further investigation. Now, maybe some of you, when they heard, well, let's create a stack profiler, they might say, wait a second, isn't there something like this already? And it turns out, well, there's kinda something like this already in that we have this tool called Zen CTX, which is part of the Zen tool suite. And it is a generic introspection tool for Zen guests. And one of the options is actually to print a call stack. And, well, then when you think about it, you can just run Zen CTX over and over and over again, and then you have a stack profiler, right? Well, kind of. That was actually the point where I started from. There was a blog entry by Brendan Gregg about a year ago where he talked about this, and that was the starting point. But there are a couple of problems with this approach. Well, probably the biggest problem here is that Zen CTX is slow, like really slow to produce stack traces. When you measure it, even on a fast Xeon 3.7 gigahertz machine, you end up with something like 3 milliseconds per stack trace, which doesn't sound so much, but once you start sampling your application a lot, that really adds up, right? So at 100 samples per second, you're looking at 300 milliseconds per second just spending tracing. Now, I'm not really saying like Zen CTX is a bad tool. It's just really not designed as a fast profiler. It's a generic introspection tool, right? The problem is that for a profiler like this, performance isn't just a nice-to-have feature, because we have to interrupt the guest all the time. We have to pause it, then create a stack trace, then unpause it, because otherwise we run into all sorts of race conditions where the guest changes the stack while we are walking it. And then if you have to pause and unpause all the time, overhead can really influence the results that you see, because it might change the application or the unikernel behavior, especially if you do something like network I/O, for example. So low overhead is really imperative to use this tool and get credible results, especially if you want to do it in a production environment. So the first question that I had to ask myself was, do I want to extend and or slim down Zen CTX, or do I want to write something new from scratch? And well, the talk title is kind of a spoiler of what the end result was, But I did in the beginning try to extend Zen CTX, and I'll show some numbers about that in the evaluation section at the end of the talk. Now, for a stack profiler, what do we actually need to make it work, just in general? Well, we need access to the registers, because we need to have the instruction pointer that tells us where we currently are in the code. And generally, you also need the frame pointer to tell you the size of the stack frame so you can find previous return addresses and actually walk the stack down. That part is pretty easy because, well, we have the get vCPU context hypercall, which just gives us, among other things, all CPU registers of the vCPU of the guest. We also need to, of course, access the memory of the stack so we can actually read the information in it. And it turns out that this is actually the complicated step here, because to read the addresses or the content of the memory, we need to map the memory over from the guest that we're profiling into the guest that runs the profiler. So in our case, it's typically DOM0. And for that, we need to do address resolution because the mapping functionality wants machine frame numbers. And well, although we're basically introspecting kernel code in the end, there's of course still the thing that the kernel, the unikernel runs on virtual memory. So we have virtual addresses and we need to do a virtual to guest physical address resolution. And it gets a bit worse because even if your guest is using something like PVH to have hardware support to do that, as the profiler, we can't really because we're looking in from the outside. So it turns out that we basically need to walk the page tables manually ourselves to find the information that we need. And then finally, what that gets us in the end, if you produce such a stack trace, as a first step, you only have a bunch of memory addresses. So we need to resolve these memory addresses into function names so we actually can see what's going on, right? And for that, we need a symbol table. And that thankfully is easy again because we just have one single binary for our unikernel and we can just run a tool like nm on the ELF to create the symbol table and then use that for the address resolution. Now, I assume that a lot of you people know how that works in detail, but I still want to go over it pretty quickly. How does a stack trace work on a basic level? So you start with the instruction pointer, which basically tells you where you currently are in your code. And for this example, I basically implicitly do the resolution into function names to make it a bit easier to understand what's happening. So the instruction pointer would tell you, okay, I'm somewhere in function 3, which is the topmost function that you see on your stack. And then what you typically do is you use the frame pointer, which gives you the base address of your current function's frame. And from there, you know where to find the return address, which tells you what you were called from. In that case, function 2 calls function 3, so we put this here. And then you can, since also the previous frame pointer is on the stack, you can just walk back to the previous frame and do the same thing again, and then you see that function 1 calls function 2, for example. And this works a bit like a linked list where you just traverse all these saved frame pointers until in the end you reach one that says, well, null, there's nothing else left, and then we know that our stack trace is complete. Now, as I said, this only really works if we have access to this memory on the left side here. So we need to map this over, and for that we need to walk the page tables. And I want to give you an example of how this works on x86, 64-bit. Uniprof also supports 32-bit on x86, and it also supports ARM, at least for those ARM machines that we tested it on. Okay, so you have a 64-bit virtual address, and what happens is that actually some bits of that, the most significant, aren't even really used for the address resolution these days because of hardware constraints. The first thing that you need is you need to find the entry point into the first level, the most basic level of your page table, and that is in the CR3 register, which basically gives you a base address to a page table. And then you take part of the virtual address to find an offset in that memory area, which then gives you here in red a certain memory content that is an address that works as a base address into the next level of the page table, where you again take a bit of the virtual address and do this over and over again. until you've done this in the case of 64-bit 4 times. And then finally, this blue area gives you the more significant part of the physical address, and the rest of the virtual address is then used as a lesser part of the physical address. Now, when you look at this, you see that not only do we need to map over this guest physical address memory here on the right, but we also need to map over all the parts of the page tables because we also read from them, right? So there's a lot of mapping going on. So as a very naive implementation, you would have 5 maps that you need to do for every single entry in your stack trace, so per function, for example. But of course, page table locations don't really change much over the course or the lifetime of a VM. And stack locations also typically don't change that much, except if you have, for example, a unikernel that uses a lot of threads, so a lot of new stack locations appear and disappear. And that means that there's definitely some chance to do some effective caching here, where we just keep all this around to speed up the address resolution that we need to do. And then finally, just to go through all 3 points that I mentioned in the beginning is, as I said, we still need to resolve the memory addresses that we get from the stack walk to function names. And as I said, that is kind of trivial because in a typical unikernel, the virtual addresses that you have in your ELF file are mapped one-to-one into the unikernel address space, so that you can just use a tool such as NM, but also I guess readelf or whatever, to create a symbol table, and then you can use that for every time you run your unikernel. Of course, to do that, you need an unstripped binary, but if you really want to strip your binary, just do this first and then strip it afterwards. Now, what does all of this get us? So we have all these stack traces lying around, and we need to kind of analyze them. And one really nice tool for that is flame graphs. I'm not sure, who's aware here of flame graphs? Okay, that's good, a couple of people. I'll just quickly try to explain to the others how this works on a basic level. I'm sorry that the font is very small, but what you can see here is on the y-axis, basically, what you see is stack traces that you found. And for example, here at the very top, you would have something like netfront transmit pbuff, which was called by netfront transmit and so on. And basically each layer is one step in your stack trace. And then the x-axis gives you an idea of the relative runtime. So all call paths that are the same in your samples are basically aggregated, and the width tells you something about the relative runtime of these call paths. So in this example, you could see that, for example, this number 1 is netfront transmit pbuff, which shows up quite a bit. Then at number 2, we have netfront rx, which is really this part there, number 2, where nothing is on top anymore. But on 3, we also have the block front AIO poll. And so these would be 3 typical heavy hitter functions in this example. And when you look at these names, some of you might have figured it out already. It's just a small mini-OS test unikernel that's doing some network communication with LWIP. Oh, what I forgot to say, sorry, this tool is not something that we created. This is a tool that is becoming more and more popular, which was designed by Brendan Gregg from Netflix. And you can find the implementation online at GitHub, and I'll show you a link afterwards so you can have a look what you can use it for. It's especially useful for stack traces, but you can also use it for other kinds of visualizations or data that you want to visualize. Okay, so now let me show you a couple of performance numbers to give you an idea how Uniprof performs. As I said, originally I looked at Zen CTX and tried to figure out whether it would be more useful to just improve the Zen CTX tool for our requirements. So one thing that I figured out pretty early is that this address translation and mapping that I talked about, that Zen CTX really did it in the most straightforward way, where it would translate and map memory addresses on every single walk for every single address, which gave you a huge overhead. And of course, as I said, the solution here would be to just cache the memory that you have already mapped, so you don't need to do this all the time. Another thing that I saw was that Zen CTX uses linear search to do address resolution. So it goes through all the symbol table linearly. And of course, if you want to be faster, you can do something like a binary search. Or actually, you don't really necessarily need to do the resolution while you're doing the stack tracing at all. You just save all the memory addresses, and then once you're done, you go and just do the address resolution offline and save all that overhead. And so to give you some idea of what that gets you is, you can see here on the left, so all these numbers, unless I say otherwise, were run on a Xeon CPU with 3.7 gigahertz speed, and on a relatively simple MinUS unikernel. So what you can see here is Zen CTX, as I said before, uses about 3 milliseconds for a single stack trace. And just caching the pages, as this first bullet says, already gives you a huge improvement, so you're down to like about 40 microseconds immediately. And then if you do implement some other improvements like binary search and so on, you can maybe get this down to 30 microseconds or something like that. But that's already getting kind of hard, and compared to the caching, that's almost a drop in the bucket already. On the right side, you see the overhead that profiling in a unikernel introduces. And I measured that basically by having a MinUS unikernel that would run for a certain amount of time, and then I would run it, and then I would run it again while profiling and would see how much longer it would take to run. And you can see that for Zen CTX, for example, the overhead is really huge, and already at about 100 samples per second, you run into nearly 40% overhead, and faster sampling speeds are simply impossible. And then with the optimized version, you're already down to below 1% of overhead for 100 samples per second. And if you really want to do very dense sampling, you could go up to 10,000 and still have a lower overhead than you had before. Now, the problem is I realized the more I was changing Zen CTX, the more I was moving away from what the tool actually did. So I added some functionality here, but then I threw out some other functionality there to make it more lean. And all of that really made me think that it would be better not to just change this tool over and over again, but I then decided to basically take the lessons that I learned from this and rewrite a new tool, Uniprof, from scratch. And the remaining numbers are basically about that. So, as I said, Uniprof. So we already get almost 100-fold improvement over Zen CTX by these performance improvements that I showed before. But we definitely can still do better. So Zen CTX uses the Lubec C library for hypercalls and memory mapping and so on. But with Zen 4.7, we had these new additional low-level libraries introduced that are more specific to certain tasks, like libzencall for hypercalls and libzen for memory mappings. And these are actually also quite a bit faster in their runtime, and that alone already gives you another significant reduction of about a factor of 3. And you can see that here. So basically the first version of, or the version of Uniprof that uses Lubec C would take about 35 microseconds for a stack trace, while the version that uses libzencall and libzen for memory would only use about 12 or so. And of course, the current version of Uniprof supports both, so you're not required to use a newer version like Zen 4.7 or newer. You can always go with Lubec C for older versions of Zen. And again, you see this faster stack walking time translates into lower overhead. Another thing that we were interested in is that we wanted to also use our profiler on ARM. And as far as I know, at least last time I checked, Zen CTX didn't really have proper ARM support. But for Uniprof we did this. And most of the code is actually, of course, very similar. The main challenge here is that the page table design on ARM looks very different from the x86, so we needed an additional page table walking implementation for this. Now, first, when you look at these numbers, it looks like ARM is, the ARM implementation is a lot worse than the one on x86 by a factor of maybe 4 or something. But what we have to keep in mind here is that this compares a bit apples and oranges. We have to be careful here. So the x86 numbers were run on a Xeon with 3.7 gigahertz, while the ARM numbers were run on a single board computer, a QB truck, which is a Cortex A20 at 1 gigahertz. So of course it will be slower. And the thing is also that, of course, since the CPU is slower, the same sampling rate gives you an effectively higher resolution because there's simply not that much happening in the same time, amount of space. So we can say that more or less on ARM, this is also running almost at the same performance numbers, probably. Now, I mentioned once or twice here that we need frame pointers to figure out where the stack frame is and to actually walk the stack and find the previous functions that were called. And that is the typical approach that you use in stack profilers. But you don't absolutely require those. And one thing that we were interested in was to also have a profiler that would work without frame pointers. One good example why you wouldn't have one is that you compile your code, like in GCC, for example, with FOMIT frame pointer, which just repurposes the frame pointer to a general purpose register, and that can give you performance improvement because you have one additional register available. Now, of course, then you need to figure out where the information is in your stack in some other way. And one way to do this is we use some other kind of stack unwinding information. The nice thing is this stack unwinding information should already exist, for example, if your unikernel is coded in C++, because it needs this additional information to do exception handling. Then you would find this information in your ELF file in these EH frame and EH frame header sections. So you can just check easily whether your code already supports it. Otherwise, you can just give your compiler a flag to create this if it's not created automatically. The nice thing is this doesn't change the performance of the code at all while it is running. It just increases the binary size. And the whole thing is defined in a pretty lengthy standard called the Dwarf standard to go with the ELF file. And well, the thing is, how does that actually work? And I looked at the standard, and the more I looked into it, I figured out that there's actually quite a bit of intricate design going on there, and it definitely is outside of the scope of this talk to go into detail here. But on a very basic level, what it creates is basically a lookup table that just says for every program address that you can reach in your code, it saves in a lookup table the size of the current frame. So whenever you create a variable, for example, the size would increase. And it locates or saves the location of those registers that it would need to restore when it returns from the function because the registers were clobbered. And that, for example, could be a frame pointer or whatever, the instruction pointer, which is very important to figure out what the return address is, and so on. Of course, it's a bit more involved than that because a simple lookup table would obviously be huge. There's also an index that allows you to quickly find the correct table entry. And as I said, this is quite important and was originally, I think, developed for exception handling, where if an exception occurs, you really need to immediately jump out of your function and basically go back your call chain to figure out where an exception handler would be. There are several library implementations around that help you with reading and interpreting this unwinding information. For Uniprof, I decided to use libunwind. Actually, a libunwind that I extended and patched so that you can use it with Zen. So in that case, we now have a libunwind that basically allows us to unwind stacks inside a different domain. And maybe that might be interesting for one or two people here, without any connection directly to Uniprof. Now, to show you some numbers here, this is really a bit of a work in progress at the moment, and what you can see is that the performance at the moment really isn't so great. So we have an increase of easily like about fourfold at the moment. And the reason here seems to be, after looking into this a bit more, is that Unwind simply does a lot of stuff that we don't really need just for walking the stack, because it already in the background does a full reconstruction of all registers in some ancillary memory, so that when you then would say, yes, please unroll to here, that part would be very fast. So I'm pretty sure, though, with a different library, or just an own implementation inside Uniprof that only does the steps that we need for a simple stack walking, we could probably improve the performance here quite a bit again, and maybe not get quite back to this blue bar, but much closer than it is at the moment. I think at the moment, especially if you're not doing a lot of sampling, very high sampling rates, I think this implementation is still good enough to be run already, but of course this is definitely an area for future work to have some improvements there. And with this, I want to come to the end of my talk. You can see here some links. It's the GitHub links to Uniprof and this patched Unwind library that we created, and also a link to the flame graphs if you're interested in how this visualization tool works. Thank you, and are there any questions?
Any questions?
So on ARM, the processor provides a page table walk feature that I think Zen probably uses, and it might make available via a hypercall accessible via maybe libc or something.
Okay.
Is that of any use?
I have to admit that I'm not really aware whether there's something like that in libc. I mean, there's a good chance. In that case, I might just have not seen it. And the one thing that I would have to check is whether you run into similar constraints as with the hardware-supported page table walking if you use PVH, for example, on x86, where it's not really possible to do it from the outside if you're not running the domain yourself at this point in time. But
I think Zen could probably, I mean, you probably need Zen to make the relevant CPU operations anyway.
Mm-hmm.
So
I think
Zen
that's
could
a good
probably
point.
do that for you. I do know that x86 Zen obviously has a software page table walker in it,
Right.
and I think ARM Zen does not have a software page table walker
Mm-hmm.
and just uses the CPU feature.
Yeah, that definitely sounds interesting. Maybe we'll talk about this in a break. And yeah, thank you for the hint.
I mean, it might be slower because it obviously you'd have to make a hypercall, so that might be slower.
Right, right. I mean, but it would be, you're right, it would be worth a try to see whether it gets us anything.
I believe that you need to be in the context of the, in this context where you want to walk the page tables, because it's talked on a TTBR register, which holds the base of the CS3
Okay, so if it
equivalent.
depends on that, then it will probably be a problem, because it's been a couple of months since I wrote the page table code for ARM, but I think what you need to do is you also need to use the get vCPU context hypercall to get these foreign TTRS registers and then walk manually from there.
I mean, if this was done in a hypercall like Ian suggested, then switching with what page table is in use in order to do the walk should not be a big problem.
I don't know. So the problem is you would need to do an awful lot of switching back and forth, right? Because you
Yes,
wouldn't.
I mean, but that might still be faster than doing a set of maps and unmaps.
Right. It would definitely. I'm pretty sure you're right that it would be faster than a set of maps and unmaps. But as I said, you typically can amortize a lot of that overhead by just doing caching of the information. So at the moment, Uniprof, whenever it does a map, it basically saves what virtual address memory area is this, what machine area was this mapped to, and especially for the page tables, that works pretty well because they don't really change.
Yeah, sure.
Yeah.
So it's
Right. It's a good point. It might actually be something that's definitely worth trying out to see what the difference is to look at that.
It very much depends on the effectiveness of caching. If caching is really very efficient, then
I mean,
the hardware
one
will
advantage
help.
that I see with this is that, of course, at the moment, the manual implementation that I have really is only tested for those ARM devices that I have. And as far as I know, with ARM, again, you have this thing that different ARM processors might use slightly different implementations. So maybe a more generic implementation using the Zen code might be more widely applicable for more devices, for example.
Okay, and I've got another question regarding the use of dwarf unwinding. How much?
For the use of what?
The dwarf unwinding.
Okay, yes.
How much assembly code is involved in a typical unikernel?
How much assembly code is involved in the unwinding library?
No, in the unikernel itself.
Oh, well, I guess that depends on your unikernel. I mean, typically the ones that we use, all the main functionality is written in C, for example, and only the parts that would be required in assembly code would be assembly code. So just very basic initial stuff.
I suppose you guess what I'm getting at.
Yes, I know. Yes. That's
the question is the annotations to the assembly code.
That's a very good question. I honestly would have to check. It's something that I didn't really think about because it never came up for us. But I'd have to check what, I mean, in the end, GCC, or at least the assembler part of GCC, also transforms the assembly code into machine code, right? But I'm not sure whether it interfaces at all with this unwinding information. That's a good point.
I'm not sure I understood. I mean, what I'm referring to is handwritten assembly.
Right.
Everything the compiler does is properly annotated. We can assume that at least, unless the compiler is buggy.
Right, right.
But handwritten assembly obviously cannot be annotated unless the human has created the annotations. And in the Linux kernel, these manual annotations have been removed for being undue complexity. And then additionally, as you mentioned, dwarf unwinding provides information for all save restore registers, not just the ones you're after.
Right.
So recently, a first cut at a simplified unwinder has been put into the Linux kernel, which might be worthwhile considering for your purposes as well.
That's a good point. Do you know when about that happened?
For the 12.
Okay, thanks. I'll have a look.
It's called ORC Unwinder.
Okay.
It still has a couple of rough edges, obviously, but it might at least help.
So it's being used in the Linux kernel also, for example, to do stack traces when a bug or something happens, as opposed to this previous thing where it just looked at the whole stack?
Yes, and in particular, I mean, the main goal is to avoid having to have a lot of manual annotations in assembly code.
Right.
There are some that are required, but otherwise there is a tool which analyzes the assembly and generates annotations on a machine basis.
Okay, that sounds very interesting. I'll have a look. Thanks for the hint. Any other questions? Doesn't look like it. Okay.
So, yes, just time is over, so
Yes, I think
there's no
if-
further
if there are
questions,
other
so you're
questions-
just in time.
Right.
Very
If there
fine.
are other questions, I'm here today and tomorrow, of course, you can always talk to me. Thank you.